Hi, welcome to another video. It's the 3rd of January today. Hope you had a good Christmas and New Year celebration. So this is a quick video, quick guide for beginners. Some microelectronica in their GUI, their visual TFT, don't provide any decent sort of rotating dials or clock faces or anything for this Fusion and their 32-bit microcontroller. Bit of a shame because it's well capable of delivering, a rotating disc. So because of that, I've had to make my own. Now, some of the original code I found years ago. I think Kevin Dara had produced just a rotating line, and I've incorporated that. Then a small routine to center it in any display, and just obviously give us a rotating. Whether it's a knob or rotating gauge, something like that. So this is for beginners. So try and not make this too long, but it is fairly complex. So if you're a novice, that's a circle, that's a circumference, this is a radius. Now when you're mapping out a circle, you start at sort of 3 o'clock. So this is cosine and sine. So cosine's first. Cosine is the x-axis. Sine is the y, sort of amplitude, and I'll demonstrate that. So here we're starting at 0 and we go anti-clockwise. So if you take the diameter, this is the radius, but if you take the diameter, put it around the outside, you need roughly 3.14 of the diameter to complete the circumference. Now I say roughly 3.14, so 3.14 is pi. So we've got a pi symbol there. Now pi is actually an irrational number, which means it's never ending. So if you use a diameter, wrap it around the outside 3.14 times. If you zoom in close enough, you'll have a gap. So you have to add another little bit and another little bit, and it goes on forever. If you add more than 3.14, like 3.15, it's already too big. So that's where pi comes from. The diameter times 3.14, or pi, that's rounded down to 2 decimal places, will give you a circumference. That's the radius, starting at 0, which is 3 o'clock. So on the x-axis, from the middle to the right or the left, we've got the x's 1 and then nothing. So across 1 and up and down nothing. Now what I didn't see explained was where does a 1 come from, and I'm messing about. This 1 is the radius from the center to the circumference. If you make this 2, it means you're doubling the radius, and you'll come out here. So I can possibly show that if I've got time. So 1 is 1 radius. The sine is the amplitude on the y-axis. So cosine of x left to right, and the sine of y up and down. So if we rotate this anti-clockwise at 12 o'clock, we've gone pi divided by 2. So that's roughly 1.57. Go around to 9 o'clock, that's pi, so that's 3.14. Come back round, we've got 2 pi. Now just to confuse you further, the cosine function in microelectronica's library, cosine of x and y, they give you radians, not degrees. So the radians in degrees, if you take this radius, stick it along the outside, and then where it ends, draw another radius. That inner angle is 1 radian. So you can see moving up to here, where it's not 1 radian, so we're dealing with minute amounts of movement in degrees. Well, so I've just programmed this, so we are now increasing and decreasing the cosine of x, and we're not changing y. So the amplitude isn't changing, we're just changing the x-axis, and you can see there it comes up to 1, down to the middle, and then back out the other way, and you can see we got negative. But this is -9 point, but look at that E, so exponent -1, so you move the decimal place so it's less than 1. Obviously 1 is the outside, and then this will be -1. It's probably going a bit too quick. Yeah, I didn't see it, but went up to like -9, but that point needed to go over one place because there's E1. So this is just moving the cosine of x on the x-axis. Right, now let me program it, and we'll vary the amplitude and not the cosine. Right, so I've just reprogrammed this to now show the amplitude, so the sine of y. So we're increasing y, and it's not like the x-axis, the cosine of x, where we get a line moving backwards and forwards, because the sine y, the amplitude, is defined by the cosine of x. So as x moves across, it's obviously plotting y. So we need x to plot the amplitude of y. Unless of course it was nothing, then we just have a dot in the middle. So this is the sine of y, this is the amplitude. So as this is coming down, we'd be plotting this second half, and that would be coming up to 0, and then starting to map out the top half. Then come around here, we'll be coming down to 0, and then down to here. Yeah, I forgot to put the value here. So this down at sort of 6 o'clock is 3 pi divided by 2, or 4.712. So if pi is 3.14, 2 pi over here, when we've mapped a complete circle, 6.28 or something. Yeah, so down here it would be 4.712. Forgot that bit, but these numbers are in the way. Right, so in summary then, the cosine of x is mapping the x-axis, and the y is the amplitude from top to bottom. So we need x to give us our y. Otherwise we just have that flat line that we started with, which is just x moving across the screen. And 1 is the radius from the centre to the outside. If it was 1.5 or 2, the radius would be out here, so that's why this is always 1. Up here, it'd be nothing, and then y would be 1, so 1, 0. Then down there, -1 and 0. And then down there, 0, -1. Or, so nothing, pi divided by 2, pi, 3 pi divided by 2, and 2 pi. Right, so this is me not messing about with anything. That's just plotting the radius at different angles. So obviously using cosine of x and y to plot different angles in relation to the previous. You can obviously use cosine and sine to get angles of triangles and that sort of stuff. Right, so just before I come off this and show you the final gauge, I will put a link in the show more to the whole program. I'm not going to run through the program. I'll dump the program somewhere, I think a couple of files, and yeah, you can browse, and if you want to know more, leave a comment. So at the moment this is drawing the red line, and then it's drawing in black immediately afterwards. And don't forget, this is giving us the radians, not degrees. So instead of clearing the cosine x and sine y, I'm inverting these, so swapping them about. So the x is coming before the y when we clear it, and we get this result. Pretty smart. So what you need for this program, this gauge I'm going to show you, is just a microcontroller that can handle a float or a double. It's got to have big enough memory to handle, you know, decimal places. See if I can speed this up a bit. There we are. This is how quick it is without having to display, you know, numbers and text as well. So the pause is when the x-axis gets all the way across one side. You can't keep on going because it doesn't exist, so it stops and starts coming back the other way. So cosine of x on the x-axis, sine of y on the y-axis to give us the amplitude. Now I'll show the gauge. Well, hopefully we're not getting too many weird effects with this camera looking at a display that's, you know, flickering. So this is just a bitmap in the background, and I've just taken that same x and y and put it on top of a bitmap. So the bitmap is 320 by 240. Now what I've done in the program, you can have this function on any screen size so long as you keep this pointer square. So this is 320 by 240, and I think in this example I'm running now, I've set up the screen size, the sort of virtual screen size, at 117, so this is small. This could actually come right out here, but it'd be too big for the gauge. And also what I've done, so these are only 10 degree increments, so there's 10, 20, 30, 100 there. What I've also done is put an offset in there, so no matter what you want, if you want this as a temperature gauge, Rev Counter, Speedo, voltage gauge, there's a little function, I've written a little algorithm to keep the needle coming up to 100% no matter what you put in. So let's say you want this as Rev Counter. Let me change this number here to 7,000. You just change the maximum number you want and program it. So it's at 170 at the moment. Let me put in 7,000, and I don't have to adjust anything else. I'll leave it on while it programs. See it programming up here. There we are. Now it's not just a case of putting 7,000 in there, because this is counting in steps, and it's got a flow of 170 steps. So we had 170, I've now put in 7,000. It's got to work out the steps to get from 0 to 7,000. Now there's actually a delay, so you can see this coming up sort of gently, and less of a delay coming back down. There's a 17 millisecond delay going forward. Right, so now what I'll do, also in this program, if you've got a microelectronics fusion board, there's an ADC input here wired to a pot. So I've actually set that up in this demonstration program. So you can obviously label this what you want. Let me change the program to the, instead of it just counting internally, it uses this external ADC function. Back in a minute. So I don't want to set up the screen capture just for this little bit. So if you want to download this sample program for the gauge, there's two functions up here. So cosine of x is a current value plus min value, and current value plus sine of y is sine current value plus min value. This is for the ADC, and this one is just to have it counting internally. And what I'd previously remmed out, but now I've I'll put these statements in the 2 backslashes to remove it. So I've now undeleted this ADC. I now need to pick this line of text for the ADC. So undelete this, and I've already deleted the other one. So it says here incorrect. No, correct here for speed or correct here for ADC. And I think we're good to go, so I can just program that now. Oh, and also the middle, all these delays, if it's going forward and backwards by itself, you need to just remove all that. So yeah, just a backslash, asterisk, and the opposite here to, get rid of all that middle section. So now I'll program that. Right, that's finished, and I've forgotten to put in a delay, because this, once you incorporate this ADC, it's very quick. And you can see that scanning there, hopefully. Let me put in a delay, something like 50 milliseconds, I think it is. I've got 30 here. Well, I'll put in this 30 millisecond delay, and we'll see how responsive it is. So while it's programming, so because this is very capable of running this gauge, or Rev Counter, temperature gauge, Speedo, fuel gauge, why do Microelectronica not make those GUIs available for the PIC microcontrollers? I'm a bit annoyed because we have to pay the same money as like someone who has the FT800 or the ARM microcontroller, yet they get more functions and we get bugger all. Right, this is the ADC. Hopefully you can see me turning that, and there is no delay at all. So if I flick that round, see 0, 7,000, set it in the middle, somewhere there, and that's reading the ADC, 10-bit ADC. Look at that, so you could use it as a rev counter, or if you need a responsive gauge. You zoom you in a bit. So I'll move the ADC, the potentiometer. There's no delay there at all. Obviously come up slow. So this is a bitmap. So one little tip, if you import your own bitmap and you're drawing the needle in red, you need to then draw it again in the colour of the background. Now this was blue, so I put blue into a sort of while one counter, or like a for loop, and it would count up, and blue starts at 31, so go 32, 33, 34, and when I couldn't see the line anymore where it had been, I copied that number, and I actually got up to 1,200, I think it was. Well, you'll see in the program, so unsigned into colour 1022, I couldn't see the line anymore where it had been when the counter got up to 1022. So a little tip, if you're importing your own gauge, find out what colour the background is, if you haven't drawn it yourself, get a counter counting, and then when you can't see the line anymore where it's been, that's your number. So that's the ADC. Just once again, so I'm turning this up here. So that's 7,000. You can make 100,000. You'll see in the look at the C file, there's a function in there to do all the work. There's lots of functions so that you don't have to map everything out. I've done it all for you. You just put in your maximum number for this and your real screen size, and the program will do the rest. I'll just show you, so hopefully you can see this. Not getting too many effects off the monitor. So for it to work, I'll forget the pi. Some of these bits aren't used, as well as measuring triangles. So we don't need this pi, for example. So look, the real width, 320 by 240. For that pointer, I've got it set as a square screen, 117 by 117. If I got rid of the bitmap, I could make this 240, get a massive pointer. And depending on the screen, this program, this bit here, will always keep the dial in the middle of the screen. And this bit here calculates the ADC depending on what your voltage coming in. It works out the throw of the gauge, works out your min and max, and gives you the difference. See, look, capture ADC, and then so we've got steps. How many steps on the gauge is 170 divided by 1023, which is the ADC, 10-bit ADC, divided by min and max, and then current value is a capture divided by 170. But it's all done for you, so leave everything as it is. Just change your TFT if you've got a different TFT. Obviously the ADC, the init for the ECU, TFT. I'll add the files that you have to include for the picture. I like this hypotenuse, adjacent, opposite. You don't need any of that, delete them. Well, so just before I go, one final look. So it's still set at 7,000, but you can set it whatever you like. 10, 5, 2, 100,000, probably up to an int, I think, so 65,000. And this is it running. Small millisecond delay when it gets to the end, stops. But that's a 2 millisecond delay. And actually this is slower than the ADC. That ADC, I couldn't believe how quick everything becomes. So yeah, PIC32, very responsive. Yeah, so this PIC32, I think there's 1 mega samples per second on the ADC. Fantastic. But yeah, so this is very capable of driving a gauge and picking up the ADC. So it used about 1% of the RAM. So why do we not get a decent GUI? Yeah, if you've got an ARM, you do. Only Microelectronica can answer that question. Anyway, hopefully you enjoyed this. Thank you for watching.